Hi friends, welcome back to Edupedia World. In the last lecture, we discussed about phase changes. Today, we will focus on a particular aspect of phase change, which is the latent heat to carry out the phase change. We'll understand what latent heat is. We'll see what specific latent heat is, and then we'll jump into the special or the specific latent heat, specific latent heat of fusion, the specific latent heat of vaporization. We will understand what those terminologies mean. We'll also see the units for these things, and then in the next lecture we will solve numericals from the understanding which we gather in today's lecture. So let us see what today's lecture has to offer. In today's lecture, we will understand the concept of latent heat, and then we will pursue it further to understand specific latent heat. So let us begin with what is latent heat. Latent heat. The term latent means hidden. Its dictionary meaning is hidden. So it somehow means hidden heat. What do I mean when I say hidden heat or latent heat? When we heat a material, normally what happens is that the temperature starts to increase. So external manifestation of heating the material is increase in temperature, right? You keep on heating, the temperature keeps on increasing. But once it reaches the temperature where phase change is supposed to occur, suppose it reaches the melting point of the body, then suddenly the temperature stops to increase. Though we keep on supplying heat, there is no change in temperature. Okay, so there is no way to externally understand, there is no external manifestation which says us that we are actually supplying heat. The temperature remains constant, so we are unable to visualize it by temperature change since the temperature is constant. As during the phase transformation, the heat is used, but we are unable to see where it is used. That heat is called latent heat. So latent heat is basically the heat supplied or released when phase transformation takes place. When phase transformation takes place. And why latent? Because it is not externally manifested as a change in temperature. Now that we have an idea about what latent heat is, let us see what latent heat per unit mass is. Suppose you have 2 kilograms of ice, you will require certain amount of heat to melt it. If you have 1 kilogram of ice, you will require half that amount of heat to melt it. So the latent heat for the first case is twice that in the second case. But there has to be a standard definition, something standard which will be a material property rather than the mass property. So that material property is called specific latent heat. Specific latent heat. What is this? Specific latent heat is total latent heat required by a certain mass upon the mass. So suppose 5 kg of material requires 5000 joules of heat as latent heat, then the specific latent heat would be 5000 upon 5, that is 1000 joule per kg, right? So this is basically Q upon M. So we can conversely find the amount of heat required to change a phase of something if we know the specific latent heat of that body and the mass of the body in question. So the amount of heat required would be mass times the specific latent heat, right? Now let us see some special terms related to latent heat and specific latent heat. These are generic terms, latent heat, specific latent heat. But there are special terms provided for special phase changes. How? The first thing which you will see is latent heat of fusion or latent heat of melting. So what does this mean? This means latent heat of melting means the amount of heat we need to supply to melt the material at its melting point, and latent heat of melting is amount of heat required to melt a material at its melting point. Okay. Now, as we have already discussed before, increase in heat should normally manifest as an increase in temperature. Why? Because when we supply heat, the kinetic energy of the particles increases, and the average kinetic energy of the particles is known as the temperature. Hence, the temperature should increase. But what is happening here? Here the heat which we are supplying is actually going into increasing the interatomic or intermolecular distance. So the heat increases the intermolecular distance, and as a result of that, what happens? This increase in intermolecular distance is what consumes the heat. Therefore, there is no heat actually available to change the temperature until and unless the whole phase transformation has taken place. Therefore, the whole heat which we are supplying is going into changing the configuration of the system rather than changing the temperature of the system. Hence, latent. Okay. Now let us see an example. Latent heat of fusion or latent heat of melting of ice. Latent heat of melting of ice would be, for ice it is 336. What will be the unit? The unit will be joule per gram. So 1 gram of ice requires 336 joule to melt completely into water. Fine. Now we know what is latent heat of melting. Let us see another term, latent heat of vaporization. Latent heat of vaporization, ZATION or SATION. Normally in Indian English we write SATION. So latent heat of vaporization is similar to latent heat of melting. It is also the amount of heat required to vaporize material at its boiling point. So heat to vaporize material at boiling point. Let me write BP. Okay, So latent heat of vaporization is heat required to vaporize at its boiling point. Here again, during vaporization, the temperature again remains stagnant. So where does the heat go into? The heat again goes into one, increasing the intermolecular distance, similar to what was happening here, and second, the volume increase when we change a liquid into a gas is enormous. It is manifold. So this work has to be done against the external pressure, the air pressure. So a lot of work needs to be done against the air pressure, the existing atmospheric pressure. So amount of heat is used up to do the work against the air pressure, and the amount of heat is used to increase the atom intermolecular or interatomic distances. That is where the latent heat goes, and as a result the temperature does not increase. The temperature remains constant. Now we have seen latent heat for the two most general cases that we'll encounter. Let us see a new terminology which is called specific latent heat of melting or fusion. Specific latent heat of melting or fusion. So this is defined as the heat required to completely convert completely convert 1 unit mass, which can be 1 gram or 1 kilogram of a material from solid to liquid state. Okay, so it is specific for a particular material. It is the latent heat of melting, so amount of heat required. But since it is specific of a material, we have to define it per unit mass. Okay, so for ice, it is, as we have shown here, 336 joule per gram. Let us see the units. The units of specific heat of melting will be joule per gram or joule per kilogram or calorie per gram or kilogram. So basically it will have a unit of heat and it will have a unit of mass. So specific heat, latent heat would be total heat upon mass. Okay, now we know that the specific latent heat of melting for ice is 336 joule per gram. Similarly, we have something known as specific latent heat of vaporization. That would be the heat required to completely convert 1 unit mass of a material from liquid state to gaseous state. So for melting it was solid to liquid, for vaporization it would be liquid to gaseous. And if I remember correctly, the specific latent heat of vaporization for water is somewhere around 2260 joule per gram. The units will be same for specific latent heat of vaporization too. Okay, now what is special about ice, the specific latent heat of ice? The specific latent heat of ice is quite high. This value 336 joule per gram is a lot of heat required per unit gram of ice to melt. So some practical consequences of this high value is that for example, the snow of a mountain does not melt at all at a given time, because we actually require to put in a lot of heat to melt certain amount of ice. So it is a continuous process rather than an instantaneous process to melt something. Also, when a hailstorm takes place, after the hailstorm, the temperature suddenly dips. Why so? Because the hails after the hailstorm needs to melt, and in order to melt it will require heat. The heat is extracted from the environment, resulting in lowering of the temperature of the environment. Another example of day-to-day life is that it's the burn from a boiling water is, or from steam at 100 degrees Celsius, it's much more harmful than burn from water at 100 degrees Celsius. Why so? Again, the same reason, that 100 degrees Celsius steam has added latent heat of vaporization with it. So the heat content of 100 degrees Celsius steam is much more than the heat content of 100 degrees Celsius water. Therefore, the burn from steam at 100 degrees Celsius is much more harmful than burn from water at 100 degrees Celsius. Fine. This concludes our theory about latent heat and specific latent heat. I will stop today's lecture here, but in the next lecture we will use the concepts learned in today's lecture and the previous lecture to tackle numericals, and with that we'll have a holistic picture about this whole concept. So till the next lecture, have a great day. Goodbye.